This video is going to be an overview of chapters 9.1, that section, to 9.7, and then I'll make a second video doing one of the problems, 9.7, number 8, that someone requested. So for 9.1, the title is nth roots, and a lot of these are interrelated, which is why some things I talked about this concept that was coming up and I applied it in an earlier section. So for nth roots, they actually are teaching you rational exponents, but they're trying to teach it to you in, a backwards manner, but this is 125, but I want it taken to the negative 1/3. That's the same as writing 1 over, because it's a negative exponent, and this third, that's my root, so the third root of 125. If I ask you for a cube root, they're not going to be huge numbers, so think about it. What's 0 cubed? 0. What's 1 cubed? 1. What's 2 cubed? 8. 3 cubed? 27. 4 cubed? 64. 5 cubed? 125. 6 cubed? 216. 7 cubed? 343. Those are all the ones I know. I don't know beyond 7. But 125, that's at 5. The cube root's 5. But this negative tells me it's in the denominator because it's the reciprocal. Okay? Then the cube root, again, of 64 is going to be 4, but this negative outside tells me the answer is negative. If the negative is not inside parentheses, put some parentheses, but that negative is not inside them, okay? The nth root pattern they also want to talk about is that because these are odd, they're all cube roots, they're all odd ends, n is the root number that you're using. There's only one value as your answer. If I ask for a square root, it's now even, n is now even, and we get a positive or a negative answer because 8 times 8 will get me the 64 in the parentheses. Negative 8 times negative 8 will also get me a positive 64. So both of these are possible square roots of 64. All right, 9.2 is rational exponents. So it's basically how would you rewrite this and the fact that they are the same. Woohoo! That's about it. So this is rewritten as this. That negative is on the outside of the radical sign, and then the negative tells me it's in the denominator. 9.3 for logarithm functions. The main difference between this one and 9.5, 9.6 is that they're using this as your base, x is your exponent, 7 is your answer. So 10 is your base, 7 is the argument, x is your exponent at the end. So I would do base 10 of 7 is x. That's how I do 10, 7x. To go back the other way, I would do 10 to the x is 7. So using arrows helps me a lot, so I hope it helps you. Okay, 9.4. 9.3 introduces logs because you've never seen them before. 9.4 is introducing a special log using e, a natural number, the natural number, and ln, which is the natural log. So before, you would do base 10 of 7 equals x. This is now log base e of 7 equals x. Base e happens really often and is very helpful as you go through, I think it's 9.6 is the loan somewhere. We did loans, I guess, in chapter 8, but I want to say it was 9.6 that did loans. Maybe it was 9.5. Wherever they did the approximation, maybe it was 9.4. Yeah, it was 9.4. Okay, it was 9.4 with this. They do an approximation where they make you realize E for your investment. This PERT formula is if you have a continuously compounded investment. So E happens a lot in life. It's why it's called a natural number. So to help us just not waste more time with subscripts and stuff, they do ln. And you don't have to see the e. So same thing up here. I could just do log 7 equals x because base 10 happens so often. We are in a base 10 society, so especially if you're in metric system. But this is log base 10 of 7 equals x. This is log base e of 7 equals x, or natural log of 7 is x. Both of those are two different ways to say them. And yes, know how to say them because I purposely asked that on the quiz to make sure you know how to say them so it helps you solve it. And that is a fair game as a question on the test. All right, 9.5 and 9.6, they're basically the same thing. 9.5 is trying to get you familiar with the property so you can recognize what's in your toolbox when you go and solve an exponential equation. And the main difference with this between 9.3 and 9.6 is that instead of taking log base 10 of 7 equals x, log is a function. So you can take the same function of both sides. If 10 to the x equals 7, that means any function of 10 to the x will equal the same function of x. So log of 10 of x equals log of 7, as long as these logs have the same base. Again, if you don't see those 10s, they are there. They're just imaginary or invisible. They're not imaginary, they're invisible. But if you want to write them, go for it. Write them. If you can't figure out the subscripts and the math script on the Google Doc, just put log and then put underscore and put 10. And then put parentheses the 7 or whatever your argument is. Okay, but we know a special property. Log base 10 of 10 to the x is going to be just x. And then your calculator has a nice log button where you can do x is the log of 7. Log base 10 of 7. Whatever that decimal is. What is that decimal? Log of 7. So x is about 0.845. Okay. All right, 9.7. I'm going to do a problem in the next video, but for this video, you're taking a log function and then you're going to straighten it out. So the only difference is this is y versus x, this is y versus a log of x. So it changes this scale and helps stretch out this part, but then this part of the equation still spaced out right, but it's trying to straighten out that curve. That's the goal. Sometimes it works, sometimes it doesn't.